what are you now trying to observe with the polar bear experiments that you couldn't originally do with the BICEP experiments?
Yeah, so the BICEP experiment was a refracting telescope. It was only about a 20 to 30 centimeter diameter lens. So this telescope is about 10 times smaller than it. So it wasn't a huge aperture. And in astronomy, the aperture of a telescope is inversely proportional to how small an object you can see with it. So with a very, very big telescope like the James Webb telescope or the 30-meter telescope that we're trying to build here in California and elsewhere, that instrument will have, literally thousands and thousands of times more collecting area, because the area scales as the diameter squared. The cost of a telescope scales as the diameter cubed. So to build a telescope that collects twice as much light, you need to spend 8 times as much money. And so in the early 2000s or late 90s, I realized, well, we're actually looking for a signal, this polarization signal, unlike the temperature and the spectrum signal. It's a very large scale signal. It's very large on the sky, meaning you don't need a huge telescope. And so you could make a very cost-effective, portable, compact telescope that you could put somewhere that had very low contamination. Again, we're looking for heat, effectively for heat and the polarization of the waves of light, the radiation of that heat. So we want to go somewhere cold, and the South Pole is an ideal place to go. Also, the mountains of Chile, where the Simons Array, Simons Observatory, and Polar Bear are located, is an outstanding place to be. We're above half of the atmospheric pressure that we feel at sea level here in New York or in California, where I am. So the trade-off is always between, how expensive would it be to go to space, which is incredibly expensive, prohibitively expensive in most cases, to build a telescope. We actually didn't need such a big one for doing BICEP. Now, for Polar Bear, Simons Array, which are the same size telescopes, those are reflecting telescopes. Those see light from the bouncing off of radiation, microwaves, from mirrors, not through lenses. So they have certain advantages, primarily that they can see much finer detailed signals in the microwave polarization. And without that ability, we would not have been able to make the first detection of a different kind of polarization signal that had never really been seen before around the same time as the BICEP announcement. It wasn't as big a deal. It's called gravitational lensing, which is indicative of the presence of dark matter in the universe, which has been detected and known for a very long time. Interestingly, it has not won a Nobel Prize, unlike dark energy. But the dark matter signal was the first kind of record for the field, and us detecting it was very important step forward progress in the field. And that could only be done by a telescope about 10 times bigger than BICEP. So that telescope was 3.5 meters in diameter. And then we upgraded to 3 of those. That was the Simons Array. And now we've gone back to the refracting telescopes with Simons Observatory, realizing that they actually have very significant advantages over the reflecting telescopes. And we've built 3 of them so far in Chile. They started taking data last year in 2024. And I've already gotten just exquisitely incredible data I wish I could share with you and your audience, but I can't. But it will be coming out soon. It'll be made public soon. So we have 3 telescopes that are much, much bigger than BICEP, but still much, much smaller than the Simons Array. And there's 3 of them. And the reason you need 3 of them is because each one has the ability to measure not only the polarization, but also the frequency spectrum of the microwaves. And that could tell us, unlike BICEP 2, that could tell us if we're seeing dust or if we're seeing the birth pangs of the Big Bang. And that's an extremely important distinction that BICEP 1 or BICEP 2, which is the one that made the announcement, the second generation of BICEP, did not have. They could only see one color, one type of microwave. And in the Simons Observatory, we are able to see 6 different frequencies simultaneously. And that gives us a huge ability to kind of prevent us from sort of fooling ourselves that we're seeing the Big Bang's origin, if you will, the singularity version of inflation in the event that we do detect it. And there's no guarantee that we will, but at least we can measure both the dust signal that flummoxed us before and also the potential existence of the inflationary signal, which would not only sort of demonstrate that inflation took place, not only detect gravitational waves, but also very many people believe would detect the multiverse. So we're basically building a multiverse detector, which is quite astonishing that human beings are capable of doing. And another reason why I reject this notion of, we're insignificant, we're just these, hairless monkeys on a spinning rock. There's something magical, unique, mysterious, miraculous even about the fact that we can contemplate, let alone build technology and tools to peer back the veil on the cosmos, 13.8 billion years ago.